When an ocean liner cuts through the open water, it leaves a perfectly straight, undisturbed wake trailing into the horizon. But a massive, blocky cargo ship behaves very differently. Its wake snakes side to side, and its rudder constantly shifts back and forth to correct a persistent, rhythmic swaying. Mariners call this the fat ship wobble. People often assume that turning the wheel on a ship's bridge is mechanically identical to turning the steering wheel of a car on a paved road. In reality, a ship turning in dense water is violently fighting against its own massive momentum and the tremendous resistance of the ocean. Whether a vessel can track a clean, straight line or constantly struggles to stay on course is entirely dictated by its geometric footprint and underwater volume. To see exactly how a hull's shape manipulates water pressure, we have to deconstruct the physics of the rudder, map out the mathematics of 3D hull geometry, and examine the paradoxical economics driving global shipping. Struggling to hold a straight line creates immense hydrodynamic drag. That drag burns thousands of dollars in extra fuel, turning a basic steering dynamic into a multi-million-dollar engineering problem. When a rudder sits amidships, meaning perfectly centered, water pressure applies equally to both sides of the hull. With perfectly balanced pressure, the ship maintains a straight path. Initiating a turn requires the helmsman to deflect the rudder, artificially altering the flow of water to create a pressure imbalance at the stern. Modern rudders rely on shapes identical to aircraft wings. They use a curved airfoil rather than a flat, drag-heavy board. Water forced over the curved surface has to travel faster to get around the bend. According to Bernoulli's principle, this sudden acceleration severely drops the localized water pressure on one side of the rudder. This extreme pressure differential generates enormous hydrodynamic lift. It physically pulls the heavy steel stern of the ship sideways. Moving the stern sideways does not cause the entire vessel to simply slide to the left or right. It causes rotation around the vessel's center of mass. Ship handlers refer to this as pivot point theory. To an observer, a turning vessel appears to swing entirely around an imaginary dot located roughly 1/3 of the way back from the bow. As the ship pivots, the bow continuously crashes into high-pressure still water, while the stern slips sideways through a turbulent, highly disturbed wake. The immense water pressure acting against the broad, rotating side of the hull actively tries to amplify and accelerate the turn. This phenomenon is known as induced rotation. To stop the ship from spinning faster and faster, the helmsman must apply counterhelm. They have to actively steer in the opposite direction just to arrest that accumulating angular momentum. Steering is a continuous, fluid balancing act. The rudder must constantly manipulate pressure to fight against the ocean's resistance and the ship's own rotating mass. Naval architects predict how severe this fight will be using a simple mathematical footprint: the length-to-beam ratio. A standard commercial cargo ship generally sets at a length-to-beam ratio of about 7. It is 7 times longer than it is wide. This metric dictates a vessel's directional stability, the physical tendency of the hull to track straight without needing active rudder corrections. Harbor tugboats sit at the extreme low end of this scale. They possess a length-to-beam ratio of only 1 or 2. Designers intentionally eliminate directional stability in these vessels. Having zero natural stability grants tugs the chaotic agility required to rapidly spin and maneuver inside crowded ports. Vessels on the absolute high end of the ratio scale exhibit the exact opposite behavior. The Queen Mary II ocean liner features an exceptional length-to-beam ratio of 8.4. Her sleek, narrow profile inherently resists induced rotation. Once pointed toward a destination, the hull naturally maintains a perfect straight line across the Atlantic. In two-dimensional naval architecture, the golden rule is simple. The higher the length-to-beam ratio, the greater the directional stability of the vessel. But Great Lakes bulk freighters openly defy this rule. These ships are governed by a strict geographic limitation, the narrow concrete locks of the St. Lawrence Seaway. Seaway Max vessels are built to absolute maximum dimensions to barely squeeze through these gates. If you divide their 225-meter length by their 24-meter width, you get a staggering length-to-beam ratio of 9.4. According to the two-dimensional math, these ships should be arrows in the water. Paradoxically, Great Lakers severely lack directional stability and suffer terribly from the fat ship wobble. The solution to this paradox requires shifting focus from a flat two-dimensional footprint to a three-dimensional volume measurement, the block coefficient. To find the block coefficient, you construct a perfectly rectangular box using the ship's length, beam, and draft. You then calculate the exact ratio of how much actual underwater hull fills up that mathematical box. The finely sculpted curves and tapered lines of an ocean liner leave large amounts of empty space inside that bounding box. This yields a low block coefficient of roughly 0.5. Seaway Max freighters are designed as flat-bottomed, sharp-edged rectangles to maximize cargo space inside the canal locks. Their underwater hull fills almost the entire mathematical box, giving them a massive block coefficient. A high block coefficient guarantees that the vessel physically displaces an immense volume of dense water relative to its size. As the ship drives forward, this massive wall of displaced water violently interacts with the blunt, unsculpted edges of the hull. This heavy, localized pressure easily knocks the bow off course and initiates rapid, unwanted rotation. In dense fluid dynamics, having a massive block coefficient behaves precisely like having a short length-to-beam ratio. A vessel's three-dimensional geometry ultimately overrides its two-dimensional footprint, meaning long, rectangular ships will constantly battle the chunky ship wobble. If high block coefficients strip away directional stability and ruin a ship's handling, why do commercial fleets continue to build them? This chart shows the strict inverse relationship between directional stability and fuel efficiency. Fine-line ships rarely touch their rudders, generating zero drag and saving vast amounts of fuel. Blocky ships require constant, aggressive steering, acting as a massive hydrodynamic brake that destroys fuel efficiency. This highlights the final missing economic variable in naval architecture: raw carrying capacity. Massive geographic bottlenecks force shipowners into an uncompromising mathematical trap. The canal walls dictate the hard physical limits of the vessel. Commercial operators deliberately sacrifice aerodynamic curves and tolerate horrific fuel efficiency for one simple reason: a flat, blocky hull packs thousands of extra tons of paying cargo into every single transit. The fat ship wobble is a deliberate economic feature. It is a physical manifestation of global trade mathematics, negotiated every day by mariners who must actively anticipate the fluid momentum of thousands of tons of steel.